Cookbook for the Universe 8.14.4 Challenges and Future Exploration while elegantly conceptualized. Empirical validation remains a critical step toward establishing the applicability of these principles. A. Experimental validation. Controlled experiments at subatomic scales could test the role of polarity gradients in particle interactions. Observational astrophysics could verify the influence of relative polarity and distance on celestial mechanics, particularly in systems like binary star orbits or galactic clusters. B. Theoretical refinement. Extending the framework to address edge cases, such as extreme gravitational conditions near black holes where the behavior of particles at absolute zero will refine its universality. C. Integration with established physics. Bridging relative gravity as framework with quantum field theory and general relativity may further unify the disparate domains of modern physics. 8.14.5 Conclusion. The synthesis of relative polarity and relative distance enriches our understanding of the universe by offering a unified framework that connects the microcosmic and macrocosmic realms. By emphasizing symmetry, scalability, and contextual dynamics, this approach aligns the diverse manifestations of force into a cohesive theory. As the foundation for future theoretical and experimental advancements, these principles challenge established paradigms, inviting scientists and theorists to reimagine the interconnected fabric of existence. While hurdles remain in empirical validation, the potential applications and insights promise a transformative impact on fields ranging from quantum mechanics to astrophysics. 8.15 Relative Equilibrium, a Summary. By Orion Carl Daly 1. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. Kepler's center of gravity addresses mass as matter. Relative equilibrium re-extends classical mechanics by introducing a dynamic model of gravitational interaction. While Kepler's laws provided a static framework to understand celestial motions, reimagines these relationships as dynamic and field-oriented, emphasizing energy and time as central components. This shift redefines gravitational interactions not merely as static forces but as evolving relationships shaped by resonance, symmetry, and superposition. In fact, relative equilibrium does not conflict with this view when seen as the disposition of force of an equivalent relative mass. Relative equilibrium is considered proportional between parallel entities and could, if to measure some form of Einstein's matter, be defined as EC, for an equivalent representation of relative mass with respect to matter as m. Rj is to account for a relative mass as manifold ET. Based on the inverse rule, relative equilibrium Re, a property, should be equated to a manifold S state of change. Additionally, Re can also represent the rate of acceleration of an object ET. In application, Re is to be derived from relative gravity Rg such as between, for example, the Sun and the Earth. This is where acceleration is measured at a rate represented as Re or m1d2 equals m2d1. 8.15.1 Revisiting Kepler's center of gravity. Kepler's conceptualization of the center of mass in celestial systems, expressed as m1d1 equals m2d2, was groundbreaking. It positioned celestial mechanics within a framework that treated mass and distance as balancing elements. However, Kepler's model, rooted in classical determinism, lacks the dynamic adaptability required to explain interactions across broader cosmic and quantum scales. Kepler's approach focuses on the distribution of mass and distances within a static framework, where the center of mass lies closer to the more massive body. It aligns with classical mechanics and Newtonian principles by emphasizing the relative positions and gravitational interactions of celestial objects. Relative equilibrium addresses these limitations by reframing the equation as m1d2 equals m2d1. This revision transforms the balance point into a state of dynamic interaction, where gravitational forces are not static but continuously adjusted by the relative energy and distance of interacting bodies. Here mass is interpreted as potential energy, aligning with Einstein's E equals mc, and by Orion Carl Daly 2. Cookbook for the Universe interactions are described in terms of energy fields rather than fixed masses. Kepler's vision, particularly his third law, conceptualizes the center of mass for two bodies, e.g., the Earth and the Sun, as a balancing point in a system akin to a seesaw. 8.15.2 Relative equilibrium as dynamic interdependence. Re-emphasizes the interplay of energy fields rather than isolated gravitational forces. This dynamic interdependence introduces the following principles. Time and energy integration. Temporal factors, such as the speed of light c, play a critical role in shaping the equilibrium state. These factors determine the rate at which energy fields interact and stabilize. Mass as relative potential. Mass is no longer viewed as a static quantity, but as relative potential energy encapsulated in an energy field. This redefinition aligns gravitational forces with energy-time dynamics. Covariance of fields. The balance between the Earth and Sun is not merely a gravitational pull but a result of their covariant energy fields, continuously adjusting to maintain a net zero force. 8.15.2.1 Relative equilibrium redefines the balance of forces, not as a static point. By Orion Carl Daly 3. Aka, Essay on Relative Gravity to describe the mechanics of the universe but as a dynamic interaction. It rearranges the terms of Kepler's equation into m1d2 equals m2d1. The relative equilibrium between the Earth and the Sun is expressed as m1d2 equals m2d1, which are their respective relative masses, and distances are their distances. This relative equilibrium ensures stability and adaptability in their interaction. Defining relative equilibrium. Relative equilibrium is the state where two bodies achieve a net zero force through proportional energy field interactions. Time and energy interplay. Temporal factors T equals C define the rate at which equilibrium is achieved. Integrating time as a critical component of energy field dynamics. Relativity of mass. Mass is not an absolute quantity, but is understood as relative potential energy, dynamically expressed through its interactions with other bodies. This formula represents a harmonic balance between two entities, emphasizing dynamic interdependence. Unlike Kepler's static seesaw analogy, reintroduces a mutual balance where the forces between two masses are always proportional and maintain a net zero force, e.g., m1d2 equals m2d1 equals 0. Relative equilibrium extends Kepler's perspective by focusing on the disposition of force, derived from relative mass. Relative mass is framed as potential energy, EC2, not strictly as solid matter, introducing a field-oriented view of interactions. Relative equilibrium acts as a moving constant for acceleration, suggests that the state of equilibrium between two bodies changes as their relative positions and velocities evolve over time. This would make gravity and its effects highly dynamic, rather than fixed and static. The equilibrium point, as calculated, might shift depending on the state of motion, much like how energy in a system of oscillators changes over time. Contextual field strength reconsiders the interaction between fields rather than just positions or distances. The field strength of one body is meaningful only in relation to the other, aligning with Newton's third law that every action has an equal and opposite reaction. 8.15.3 Relative equilibrium in orbital dynamics. Applying Re to the Earth-Sun system reveals a nuanced interaction. By Orion Carl Daly 4. Cookbook for the Universe. The Sun's gravitational pull and Earth's inertia achieve balance at a specific distance, defined by m1d2 equals m2d1. This equilibrium corresponds to a harmonic mean of their energy fields, ensuring stability and coherence in their orbital dynamics. This balance is not static but modulated by factors such as seasonal variations caused by Earth's axial tilt, solar phenomena like flares or winds, which introduce localized disruptions but are absorbed within the larger equilibrium framework. 8.15.4 Spatiotemporal induction. The induction coil analogy. Relative equilibrium can be visualized through the induction coil analogy. The Sun acts as a primary current source, radiating energy both electromagnetic and gravitational. The Earth behaves as a secondary coil, generating induced fields through its interaction with the Sun's radiation. This interaction introduces phase shifts, temporal delays in energy transfer due to impedance, analogous to electromagnetic systems. Harmonic resonance, oscillations in gravitational and electromagnetic fields that maintain the system's stability. 8.15.5 Applications to multi-body systems. Relative equilibrium extends beyond the Earth-Sun system to encompass galactic dynamics. Interactions between galaxies can be modeled as superpositions of energy fields, where relative equilibrium defines the balance between gravitational pull and expansion forces. Dark matter. The invisible framework of dark matter provides additional impedance, modulating the balance of forces across cosmic scales. 8.15.6 Philosophical implications. Reshifts the narrative from deterministic mechanics to relational dynamics. By incorporating concepts like harmonic mean, superposition, and resonance, it bridges the gap between classical physics and modern theories like quantum mechanics and relativity. By Orion Carl Daly 5. Aka, Essay on Relative Gravity to describe the mechanics of the universe. 8.15.6.1 Key distinctions. Static versus dynamic. Kepler's framework identifies a static center of mass that remains constant unless perturbed. Re-emphasizes dynamic equilibrium, reflecting changes in distance, energy, and relational forces over time. Conceptual scope. Kepler focuses on orbital mechanics and planetary motions, using elliptical orbits as a cornerstone of his laws. Re-expands to include interactions of energy and mass as relational constructs, integrating concepts like harmonic mean and superposition. Applications beyond the solar system. Kepler's framework is primarily solar-centric. Re-accommodates interactions at cosmic scales, including galaxies and dark matter, offering a more universal framework. Philosophical implications. Kepler's vision aligns with classical determinism, readopts a relational view, embedding phenomena like superposition and iterative balance within its interpretation of forces. 8.15.7 Relative equilibrium re and orbital placement re-explains the spatial arrangement of planets as a balance between their relative masses and distances, m1d2 equals m2d1. Larger bodies, like Jupiter, have higher relative mass m and therefore stabilize further from the Sun. Smaller bodies, like Earth, achieve balance at closer distances. 8.15.7.1 Relative equilibrium in the induction coil model. The Earth-Sun system can be analogized to a dual-pole induction coil, where energy transfer and balance occur dynamically. A. Incorporating m1d2 equals m2d1 into the coil analogy. Traditional induction coil dynamics, magnetic fields and alternating currents interact to generate energy transfer. Similarly, the Earth-Sun system uses gravitational and electromagnetic fields as its dynamic medium. By Orion Carl Daly 6. Cookbook for the Universe. Third reference frame, unlike static systems, reintroduces a third reference frame that modulates dynamically with Earth-S and the Sun-S motions. This neutral zone acts as the convergence point for stabilizing orbital dynamics. This diagram illustrates how the Earth-Sun system achieves gravitational alignment through the superposition of resonance CRS. The concentric waves represent the overlapping fields, dynamically adjusted to maintain equilibrium and coherence, while the Sun, acting as a power source, regulates AC through the Earth like an electric coil. B. Incorporating m1d2 equals m2d1 into the coil analogy. In a traditional induction coil, magnetic fields and alternating currents interact dynamically to induce motion or energy transfer. Similarly, in the Earth-Sun system, relative equilibrium defines the point where the fields gravitational and electromagnetic are balanced. However, unlike a static coil, relative equilibrium introduces a third reference frame, dynamically modulated by the movement and changing positions of Earth and Sun. This point governs the interaction between fields, acting as a neutral zone where their influences converge and stabilize orbital dynamics. C. Spatiotemporal significance of the balance point. The relative equilibrium point between the Earth and the Sun lies at a distance where perfect gravitational and inertial balance, Earth's inertia counters the Sun's gravitational pull, maintaining orbital stability. By Orion Carl Daly 7. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Magnetosphere-exosphere alignment. The equilibrium aligns with Earth's magnetosphere boundary, integrating gravitational and electromagnetic field interactions. Dynamic induction coil. In this model, solar electromagnetic flux functions as the primary current, inducing electromagnetic effects within Earth's magnetosphere. Earth, as a secondary coil, generates induced fields through interaction with the Sun's radiation, maintaining equilibrium. The solar electromagnetic flux induces currents in Earth's magnetosphere as the coil's windings. The balance defined by m1d2 equals m2d1 governs the phase relationship between Earth's rotational magnetic field and the Sun's radiation. D. Dynamic modulation of relative equilibrium. The Earth-Sun system's equilibrium evolves over time. Seasonal shifts, Earth's axial tilt and elliptical orbit modulate field interactions, slightly shifting the equilibrium. Unlike static systems, the Earth-Sun relationship evolves. Seasonal changes caused by Earth's axial tilt and orbit shift the field interactions slightly around the equilibrium point. The relative masses and distances remain constant enough to maintain relative equilibrium, but localized phenomena, e.g., solar storms, temporarily disrupt the balance, causing observable effects like auroras. Localized phenomena. Solar activity, for example, storms, temporarily disrupts equilibrium, producing effects like auroras. Yet the overarching balance remains intact. E. Revisiting the induction coil with gravity. With the induction coil analogy expands. Sun as the current source, radiates gravitational and electromagnetic energy. By Orion Carl Daly 8. Cookbook for the Universe. Earth as the secondary coil, responds to the Sun's field, generating induced currents. Equilibrium as the transformer core, defines the energy transfer and resonance frequency between the two bodies. F. Insights from relative equilibrium. Energy transfer efficiency. The m1d2 equals m2d1 equation quantifies the balance of gravitational and electromagnetic energy flow. Stability point. This ensures dynamic stability amidst fluctuations such as solar winds. Gravitational and electromagnetic coupling. Relative forces and distances govern how gravitational fields influence electromagnetic interactions. 8.15.7.1 Covariance of relative forces. The dynamic interaction between the Sun and Earth emerges from the covariance of their relative forces. Inner relativity. At close range, the Sun's energy field dominates. Outer relativity. Earth's field stabilizes within the Sun's overarching influence. These forces synchronize over shared spatial and temporal frameworks, reflecting harmonic resonance between their energy fields. 8.15.7.2 Synthesis. Relative equilibrium can elevate our understanding of cosmic dynamics by integrating concepts of harmonic resonance, field synchronization, and spatiotemporal interactions. The analogy of the Earth-Sun system as an induction coil underscores how dynamic systems balance gravitational and electromagnetic forces, providing a coherent model for understanding cosmic relationships and their philosophical implications. This relationship emerges from the covariance of their relative forces, creating a dynamic equilibrium where both bodies influence each other proportionally. Their shared spatial and temporal framework reflects the synchronization of their energy fields over time. 8.15.8 Superposition through the harmonic mean. In the framework of relative gravity, superposition and harmonic mean define the dynamic interplay of forces and energies between celestial bodies like the Earth and by Orion Carl Daly 9. Aka, Essay on Relative Gravity to describe the mechanics of the universe, the Sun. This interaction is modeled not as discrete, isolated events, but as a continuous spatial-time relationship, with each body participating as reference frames in a unified system. Rather than being seen as discrete masses interacting through gravitational force alone, as a spatial time, the Earth and Sun are understood as relative masses expressed as m equals EC, engaging in a dynamic interplay as reference frames through resonance of the harmonic mean when in superposition. 8.15.8.1 Dynamic interplay as reference frames. Dynamic interplay as reference frames. A. Relative mass representation. Both the Earth and the Sun are represented as relative masses, calculated using m equals EC, where E is energy and c is the speed of light squared. The Sun is a power source and planets as coils perpetually exchange energy through alternating current-like interactions, seeking harmonic ground states much like an AC electrical circuit. These masses engage in dynamic interactions, emphasizing energy exchange rather than static gravitational attraction. 3D superposition. Planets align their energy fields in a superposition of resonances ZRS, ensuring coherence and stability across the system. B. Spatial time as a context. Instead of treating gravitational force as the sole factor, spatial time encapsulates the broader relationship of energy, time, and mass in the system. These relationships are expressed as superpositions of energy fields, resonating with harmonic balance. By Orion Carl Daly 10. Cookbook for the Universe 8.15.8.2 Harmonic Resonance and Superposition. The harmonic mean emerges as the mathematical representation of balance between multiple interacting forces and energies in the system. This principle is crucial in aligning the energy fields of planets and the Sun, ensuring coherence and stability across the system. 8.15.8.3 The Sun as a power source. The Sun is conceptualized as a power source, radiating energy that drives the entire system. Planets, acting as coils, interact with the Sun's energy through a mechanism akin to alternating current AC systems and electrical circuits. 8.15.8.43 Superposition and energy coherence. A. Energy field alignment. The planets and the Sun achieve superposition of resonances denoted as ZR, aligning their energy fields in a shared framework. These resonances ensure coherence across the solar system, maintaining stability and balance. B. See circuit analogy. Just as alternating currents in electrical circuits seek harmonic ground states, celestial bodies adjust their interactions to achieve a dynamic equilibrium. This process mirrors the functionality of AC electrical systems, where energy oscillates between components to maintain coherence. 8.15.8.5 Implications of 3D superposition. Coherence across scales. This approach unifies microcosmic phenomena like particle interactions with macrocosmic events like planetary orbits. It suggests that the same principles govern interactions across vastly different scales of the universe. Dynamic stability. The interplay of resonances allows for adaptive stability, ensuring that perturbations, e.g., solar flares or gravitational anomalies, are balanced dynamically. By treating the Earth and the Sun as overlapping reference frames in harmonic resonance, the theory of relative gravity extends beyond classical interpretations of mass and force. By Orion Carl Daly 11. Aka, Essay on Relative Gravity to describe the mechanics of the universe. It integrates dynamic systems thinking into cosmic relationships, highlighting the interconnected and evolving nature of the universe. 8.15.8.6 Sun and Earth as uniform relative forces URF. When the Sun and Earth are regarded as uniform relative forces URF, they represent dynamic systems where their relative masses interact through shared energy fields in a spatial time continuum. Their third reference emerges as a conceptual space or interaction zone where the interplay of their relative forces achieves dynamic equilibrium. Here is how their third reference can be interpreted as a uniform relative force. 8.15.8.6.1 Interaction of relative masses. The Sun and Earth, as relative masses, are represented as manifolds defined by their energy and time relationships, M equals EC. The Sun, with its immense energy output, acts as the dominant source, radiating energy into the system. The Earth, with a smaller energy-mass ratio, absorbs, reflects, and interacts with the Sun's radiated energy. This interaction creates a dynamic energy field between them, where forces such as gravitational pull and electromagnetic flux oscillate in harmony. 8.15.8.6.2 Formation of the third reference. The third reference arises naturally as a zone where the energy fields of the Sun and Earth overlap, interact, and stabilize. It can be seen as a neutral zone or a resonant field characterized by A. Energy balance. The third reference encapsulates the balance of forces between the Sun and Earth. Relative equilibrium Re equals M1D2 equals M2D1. By Orion Carl Daly 12. Cookbook for the Universe. Here, M1 and M2 are the relative masses of the Sun and Earth. D1 and D2 are their respective distances from the equilibrium point. The third reference emerges as a harmonic mean of these interactions. B. Field dynamics. The Sun and Earth's gravitational and electromagnetic fields converge in the third reference. This zone behaves like a transformer core in an induction coil, where energy is exchanged dynamically through alternating currents AC-like interactions. 8.15.8.7 Third reference frame as a uniform relative force. The third reference behaves as a uniform relative force because it satisfies the following criteria. A. Dynamic stability. The third reference ensures the stability of the Sun-Earth system by dynamically balancing their energy fields. This stability is not static but evolves over time, influenced by phenomena such as seasonal shifts, Earth's axial tilt, and orbital variations. Solar activity, for example, solar flares and radiation bursts. B. Resonance and impedance. The third reference incorporates resonance between the Sun and Earth's energy fields. Impedance within the system, such as resistance due to gravitational or electromagnetic forces, modulates the energy exchange, maintaining harmonic equilibrium. C. Superposition. The third reference can be viewed as a superposition of resonances denoted ZR between the Sun and Earth. These resonances align to form a coherent, unified force field. D. Shared energy potential. The third reference represents a shared potential energy field. Uniform relative force URF equals 4 pi r square root RET. By Orion Carl Daly 13. Aka, Essay on Relative Gravity to describe the mechanics of the universe. R. Radius distance from the reference point. E. Energy exchange between the Sun and Earth. T. Temporal factor, for example orbital period or light travel time. 8.15.8.8 Visualization of the third reference. Imagine the third reference as a virtual manifold, akin to the neutral zone in an electric field or the midpoint in a gravitational system. It is not a physical object but a conceptual space where the relative forces of the Sun and Earth interact in harmony. 8.15.8.9 Broader implications. Unifying forces. The third reference integrates gravitational, electromagnetic, and potentially other forces into a coherent framework. Energy efficiency. By acting as a transformer-like core, it minimizes energy loss and optimizes the energy transfer between the Sun and Earth. Cosmic connectivity. The concept can be extended to other celestial systems, providing insights into galaxy dynamics, orbital mechanics, and interstellar interactions. By regarding the Sun and Earth as uniform relative forces, the third reference appears as a dynamic, resonant force field that ensures equilibrium and coherence within the system. This reference embodies the principles of relative gravity, integrating mass, energy, and time into a unified framework of interaction. 8.15.8.10 Visualization of the third reference. The third reference between the Sun and Earth emerges as a virtual manifold, representing a conceptual space where the interplay of their relative forces, gravitational and electromagnetic, achieves harmony. This third reference is akin to a neutral zone in an electric field where opposing charges reach a dynamic equilibrium. The midpoint in a gravitational system where forces from interacting bodies. By Orion Carl Daly 14. Cookbook for the Universe. Balance. While it is not a physical object, this reference manifests as a spatial-temporal boundary, offering insights into how energy fields dynamically stabilize the orbital relationship between celestial bodies. Northern Lights as a visualization. One way to imagine this third reference is through the phenomenon of the Northern Lights, Aurora Borealis. These dazzling displays in Earth's magnetosphere exemplify the interaction between the Sun's electromagnetic flux and Earth's magnetic field. Interaction at the boundary. The auroras occur where charged solar particles interact with Earth's atmosphere, creating a visual representation of the interplay at the edge of the Sun-Earth energy exchange. Dynamic harmony, like the northern lights, the third reference, is a constantly shifting yet stable zone of interaction, modulated by seasonal changes. Solar activity and Earth's axial tilt. Harmonic symmetry, just as the lights display waves and patterns of energy in harmony. The third reference aligns the Sun and Earth's relative masses and energy fields into a cohesive dynamic. 8.15.8.10.1 Mathematically anchored. Using the relative equilibrium re-equation, m1d2 equals m2d1. The third reference integrates the relative masses of the Sun m2 and Earth m1, along with their distances d1 and d2. This results in a harmonic balance. A. Relative mass interaction. The Sun's and Earth's energy fields align through their respective amplitudes, forming a stable manifold expressed as m equals EC. By Ryan Carl Daly 15. Aka, Essay on Relative Gravity to describe the mechanics of the universe. B. Dynamic modulation. Seasonal and solar variations cause localized disruptions, analogous to fluctuations in the auroras. But the third reference self-corrects through harmonic mean and superposition. 8.15.9 Relative mass and superposition. In the framework of relative gravity, the Earth and Sun are not isolated entities exerting simple gravitational pull upon one another. Instead, they are modeled as manifolds, dynamic constructs encapsulating their respective properties of mass-energy equivalence. These manifolds interact not as static masses, but as active participants in a shared harmonic system, emphasizing the dynamic interplay between energy, mass, and time. 8.15.9.1 The nature of relative mass. Relative mass is framed as a manifestation of potential energy, encapsulated within a manifold that represents overlapping energy fields. The equation m equals EC2, derived from Einstein's mass-energy equivalence, is reinterpreted in relative gravity to highlight that a. Mass is not static, it is a relational phenomenon, dynamically expressed as the interplay of energy and time within the dimensional framework of space. B. Mass is energy. Both the Earth and Sun possess energy fields that extend beyond their physical boundaries, interacting harmonically within a shared spatial-temporal structure. 8.15.9.2 Interaction as a harmonic system. Rather than viewing gravitational attraction as a simple force pulling masses together, this model suggests that the Earth and Sun are components of a harmonic system. This system operates through resonance and superposition, where their energy fields overlap and synchronize, forming a dynamic equilibrium. A. Mass as potential energy. Each body's mass is an expression of its stored energy potential. The Earth's and Sun's masses contribute to a larger system where energy fields align to sustain orbital stability. B. Superposition of energy fields. These fields do not act in isolation. Instead, they create a shared reference frame where resonances e.g. CR harmonics establish a coherent and stable interaction. The overlapping fields allow for mutual influence on each other's dynamics. The creation of a virtual reference point, akin to a third reference or balance zone. 8.15.9.3 Moving beyond gravitational attraction. By Ryan Carl Daly 16. Cookbook for the Universe. Traditional gravitational models assume a unidirectional force exerted by one mass on another. Relative gravity redefines this interaction by considering a. Dynamic field interactions. The Earth and Sun influence each other's energy fields, which continuously adjust based on their relative positions and velocities. B. Energy flow through superposition. The relationship is akin to alternating current systems where energy is exchanged cyclically, maintaining coherence through shared resonances. 8.15.9.4 Practical implications of superposition. This conceptualization allows for a deeper understanding of the Earth-Sun relationship and its broader implications. A. Orbital stability. The harmonic interaction ensures that the Earth maintains its orbit within a stable range, balancing gravitational pull with centrifugal forces. B. Energy exchange. The Sun acts as a power source, radiating electromagnetic energy that interacts with the Earth's energy fields, much like an induction coil receiving energy from its primary source. C. Unified framework. The model unifies classical mechanics with principles of quantum mechanics and relativity by emphasizing the relational and dynamic nature of mass and energy. 8.15.9.5 Visualization of superposition. To visualize this concept, imagine the Earth and Sun as two oscillating bodies within a shared medium. Their energy fields overlap in three-dimensional space, creating waves of resonance that ripple through the system. These resonances act as stabilizing forces, ensuring that the system remains coherent and dynamically balanced over time. By reframing mass as a dynamic property of energy fields in superposition, Relative gravity provides a holistic view of the Earth-Sun interaction, bridging the gap between classical and modern physics while offering a compelling model for universal harmony. 8.15.10 Acceleration and relative equilibrium. In the framework of relative gravity, acceleration is redefined as the rate of change in the balance of relative forces between interacting bodies, framed within a temporal reference. This temporal constant, such as the speed of light c, acts as a fundamental limit or a scaling factor for these interactions. 8.15.10.1 Acceleration as the rate of force balance. Traditionally, acceleration A is defined in Newtonian mechanics as the rate of by Orion Carl Daly 17. Aka, Essay on Relative Gravity to describe the mechanics of the universe change of velocity over time due to a force acting on a mass F equals ma. Relative gravity, however, extends this concept by considering acceleration not just as a response to a single force, but as an outcome of the balance of forces within a system. A. Relative force balance, when two entities, for example the Earth and the Sun, interact. The forces of attraction and repulsion between their energy fields are not static. They continuously adjust as the bodies move relative to one another. B. Temporal frame. The balance of these forces evolves over time, and acceleration reflects how quickly the system adapts to maintain equilibrium. 8.15.10.2 Energy field gradients and temporal scaling. Acceleration, in this model, is proportional to the gradients of the energy fields of the interacting bodies. Acceleration, in this model, is proportional to the gradients of the energy fields of the interacting bodies. These gradients represent how the energy density of one body changes relative to the distance and energy of the other body. A. Energy field gradient. For any body, the gradient refers to the spatial variation of its energy field intensity. Larger gradients lead to stronger interactions, influencing the rate of acceleration. B. Temporal constant t, time as expressed by the speed of light c, provides a frame of reference for how quickly these changes propagate through space. The speed of light is crucial because it governs the maximum rate at which energy and information can influence the interaction. 8.15.10.3 Force of attraction and repulsion. In relative gravity, attraction and repulsion are not binary concepts but are seen as dynamic properties of the interaction between two energy fields. A. Attraction. When energy field gradients align, they reinforce one another, pulling the bodies closer together. B. Repulsion. When the gradients diverge or create interference patterns, they weaken the interaction or push the bodies apart. C. Proportionality to gradients. The strength of these forces is directly proportional to the relative gradient of the fields. Larger gradients mean more pronounced forces and consequently greater acceleration. 8.15.10.4 Temporal frame and acceleration. Acceleration depends not only on the spatial configuration of the energy fields, but also on how these configurations evolve over time. The time constant t dictates the pace of this evolution. A. Temporal dependence. Changes in force occur over a time frame proportional to c, ensuring that interactions respect relativistic constraints. B. Dynamic adjustments. As the fields adjust to maintain equilibrium. By Orion Carl Daly 18. Cookbook for the Universe. Acceleration reflects the rate of these adjustments, encapsulating both the spatial and temporal dynamics of the system. 8.15.10.5 Visualization of acceleration and relative equilibrium. Imagine the Earth and Sun as two entities with overlapping energy fields. As their relative positions shift due to their motion, their energy fields must dynamically readjust to maintain balance. This adjustment manifests as acceleration which A. Reflects the changing balance of forces as the bodies move through space. B. Ensures that their energy fields remain in sync, preventing disruptions in their orbital relationship. C. Operates within a time frame limited by c, ensuring that no changes propagate faster than the universal speed limit. 8.15.10.6 Implications of acceleration in relative gravity. Dynamic nature of gravity. Instead of viewing gravitational attraction as a fixed force, this perspective sees it as a dynamic process influenced by the energy field gradients of interacting bodies. Harmonic resonance. Acceleration ensures that the interacting fields achieve harmonic balance, maintaining stability in systems like planetary orbits. Integration of time. By tying acceleration to a temporal frame, relative gravity bridges classical mechanics with relativistic principles, providing a unified view of motion and interaction. Summary. In relative gravity, acceleration is the rate at which the forces between interacting energy fields adjust to maintain equilibrium. This adjustment depends on the gradients of the energy fields and evolves over time, constrained by a temporal constant like the speed of light c. This dynamic perspective redefines gravitational and other forces, emphasizing their relational and time-dependent nature. 8.15.11 Applying relative gravity and relative equilibrium to the solar system. Instead of focusing on mass as the primary source of gravitational attraction, relative gravity emphasizes how different forces in motion interact with each other within a given space. 8.15.11.1 Relative equilibrium in the solar system. Relative equilibrium over static gravity. Relative gravity redefines planetary motion by integrating multiple interacting forces, such as gravitational pull. By Orion Carl Daly 19. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. Electromagnetic radiation and solar wind pressure into a relative equilibrium. This dynamic state replaces the static gravitational pull traditionally used to describe planetary orbits. A. Balance of forces. Inward forces. Gravitational attraction remains the primary inward force pulling planets toward the Sun. Outward forces. Counteracting forces, such as electromagnetic interactions and solar wind, push planets outward. Together, these forces establish a balance that determines the planet's stable orbit. B. Relative frame of reference. From the Sun's perspective, planets appear as oscillating bodies maintaining dynamic orbits. From each planet's perspective, the Sun and other planets exert forces that influence its motion within a multi-body equilibrium. 8.15.11.2 Spatial induction in the solar system. A. Spatial induction engine analogy. The Sun acts like the primary coil in an induction system, generating alternating forces gravitational, electromagnetic, etc. that influence surrounding bodies. The planets serve as secondary coils, their motions dynamically modulated by the Sun's fields and their own intrinsic properties. B. Cyclic interactions. By Orion Carl Daly 20. Cookbook for the Universe. Planetary positions and velocities are not static but are influenced cyclically by their interaction with the Sun's energy fields. This feedback loop maintains the relative equilibrium of the solar system. C. Superposition and resonance. The Earth and Sun, as manifolds of energy, align their gravitational and electromagnetic fields in resonance. This synchronization stabilizes their orbit, much like two resonating bodies in harmonic motion. Planets acting as coils adjust to maintain harmonic ground states, ensuring dynamic stability within the solar system. 8.15.11.3 Phase shift and impedance. A. Phase shifts in gravitational systems. In electromagnetic systems, a phase shift represents a delay caused by impedance. Similarly, in gravitational systems, the propagation of gravitational influence could experience delays due to the space-time medium or surrounding forces. These shifts create oscillating gravitational interactions akin to alternating current systems, where the force alternates in magnitude or direction over time. B. Gravity as oscillating influence. Traditional models view gravity as a constant pull. However, if gravity behaves like an alternating current, the Sun and Earth's gravitational fields could exhibit periodic adjustments, creating oscillatory influences that maintain equilibrium. 8.15.11.4 Implications of the relative equilibrium equation. The equation M1D2 equals M2D1 mathematically encapsulates the relative equilibrium by Orion Carl Daly 21. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe within the Solar System. A. Dynamic energy balances. The Sun's gravitational pull and energy flux induce periodic adjustments in planetary motions. This dynamic balance ensures the long-term stability of planetary orbits, even amidst disturbances like solar flares or interplanetary interactions. B. Gravitational and electromagnetic coupling. The relationship between mass and distance governs how gravitational fields interact with electromagnetic phenomena, enabling seamless integration of forces within the solar system. C. Dynamic interdependence. The balance between forces pulling planets inward and those acting outward ensures stability, much like the tension in an induction coil system. 8.15.11.5 Visualization and practical insights. The interplay between gravitational and electromagnetic forces creates a feedback loop, ensuring that the system remains robust even during disruptions. Induction coil analogy revisited. A. Sun as primary coil. Radiates energy and gravitational influence, dynamically modulating planetary motion. B. Planets as secondary coils. Generate electromagnetic fields in response to the Sun's flux. Their movement reflects a balance of energy transfer dictated by relative mass and distance. C. Harmonic ground state. The system strives for resonance, with each planet's energy field aligning dynamically to maintain orbital coherence. D. Dynamic stability in the Earth-Sun relationship. Seasonal shifts and phenomena like auroras illustrate how the balance adapts dynamically to maintain stability. By Orion Carl Daly 22. Cookbook for the Universe 8.15.11.6 Broader Implications. A. Bridging classical and quantum models. By treating gravity as an oscillating influence and integrating electromagnetic phenomena, relative gravity unites classical orbital mechanics with quantum principles of resonance and superposition. B. Cosmic systems. Beyond the solar system, this model provides insights into the dynamics of galaxies, binary stars, and intergalactic interactions. C. Innovative predictions. Observing phase shifts or oscillatory gravitational effects could validate this model, offering new perspectives on phenomena like gravitational waves and solar magnetic storms. This view can offer another understanding of the solar system, depicting it as a dynamic, self-regulating network of forces and interactions that maintain equilibrium through resonance, superposition, and harmonic relationships. 8.15.11.7 Extending relative equilibrium M1D2 equals M2D across the solar system. The principle of relative equilibrium Re, as expressed by the equation M1D2 equals M2D1, provides a compelling framework to analyze the spatial distribution of planetary orbits within the solar system. This principle highlights the dynamic interplay between mass, distance, and the forces that govern planetary motion, emphasizing a balanced relationship between gravitational pull and angular momentum. 8.15.11.7.1 Larger bodies orbit further from the Sun. Mass and distance correlation. By Ryan Carl Daly 23. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. Larger planets such as Jupiter and Saturn, with significantly greater masses m, exhibit proportionally larger distances d from the Sun. This relationship ensures gravitational equilibrium, as their substantial gravitational fields require a wider orbital radius to balance the forces acting on them. Relative mass and distance. The relative mass m of these giant planets corresponds to their ability to stabilize at greater distances without losing equilibrium. Conversely, smaller bodies like Mercury or Venus with lesser masses are confined to tighter orbits closer to the Sun, where gravitational pull dominates over angular momentum. 8.15.11.7.2 Gravitational balance and orbital dynamics. Gravitational pull versus angular momentum. For planets closer to the Sun, like Mercury, the Sun's gravitational pull dominates, necessitating high orbital velocities to maintain stable orbits. These high velocities translate to higher angular momentum, compensating for the stronger gravitational forces at closer proximity. For planets farther away, like Jupiter, the gravitational pull weakens with distance. Their orbits stabilize with lower velocities, as angular momentum increases due to the planet's greater mass and distance. 8.15.11.7.3 Visualization using relative equilibrium. Equation dynamics. When expressed as M1D2 equals M2D1, the equilibrium equation illustrates that the relationship between mass m and distance d is inverse square in nature. The greater the mass of a planet, the farther it must orbit to maintain equilibrium, ensuring that the forces acting on it do not disrupt the balance. Energy fields and superposition. This principle implies that larger planets interact with the Sun's energy fields in a different spatial and temporal context compared to smaller planets. Their gravitational and electromagnetic fields are aligned in superposition at these farther distances, maintaining dynamic stability across the system. 8.15.11.7.4 The role of resonance and oscillation. Orbital resonance. Larger bodies, with their significant masses, exert gravitational influences that resonate with other celestial objects in the system. For example, Jupiter's immense gravitational field stabilizes its moons in a series of harmonic orbital resonances, while also influencing asteroid belts and nearby planets. Oscillation and dynamic feedback. By Ryan Carl Daly 24. Cookbook for the Universe. The balance between gravitational forces and angular momentum creates oscillations in the system. These oscillations act as dynamic feedback mechanisms, continuously adjusting the positions and velocities of planets to maintain equilibrium. 8.15.11.7.5 Implications for planetary distribution. Hierarchy of stability. The solar system's architecture reflects a hierarchical stability where smaller, denser planets cluster closer to the Sun, while gas giants occupy the outer regions. This configuration is a natural outcome of relative equilibrium, shaped by the interplay of mass, distance, and forces. Insights into formation. The principle of relative equilibrium also offers clues about the formation of the solar system. As planets form from the protoplanetary disk, their masses and distances adjusted dynamically to reach stable orbits, governed by the equation M1D2 equals M2D1. 8.15.11.7 Key takeaways. Mass-distance relationship. Larger planets orbit further from the Sun because their greater masses require proportionally larger distances to maintain gravitational balance. Dynamic interactions. Orbital dynamics are not solely dictated by gravitational forces but also by angular momentum, resonance, and oscillatory feedback mechanisms. Unified framework. Relative equilibrium provides a unifying framework for understanding the spatial distribution of planetary orbits, integrating principles of gravitational mechanics with energy field dynamics. This extended perspective reinforces the harmony of the solar system as a self-regulating, interconnected system where forces and motions are balanced through relative equilibrium. 8.15.11.8 Relative equilibrium in the solar system. The principle of relative equilibrium expressed as m1d2 equals m2d1 serves as a mathematical representation of the dynamic balance that governs planetary orbits within the solar system. This relationship underscores how planetary mass and orbital distance interact to achieve stability in the gravitational and orbital dynamics of. By Ryan Carl Daly 25. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe Celestial Bodies. 8.15.11.8.1 Proportionality between mass and distance. Larger masses require greater distances. The equation shows that planets with larger masses m must orbit at greater distances d from the Sun to maintain equilibrium. For instance, Jupiter, the largest planet, resides farther from the Sun, ensuring that the forces acting on it are balanced. Mercury, much smaller in mass, orbits closer to the Sun, where the stronger gravitational pull is offset by its high orbital velocity. 8.15.11.8.2 Balance between centripetal and centrifugal forces. Centripetal force. The Sun's gravitational force provides the centripetal pull necessary to keep planets in their orbits. This force decreases with the square of the distance 1d. Centrifugal force. A planet's orbital motion generates a centrifugal force, which counteracts the Sun's gravitational pull. This force is proportional to the planet's velocity and inversely proportional to its distance from the Sun. Relative equilibrium. Relative equilibrium ensures that these opposing forces are balanced. Closer planets have higher orbital velocities to counteract stronger gravitational forces. Distant planets with weaker gravitational pulls achieve equilibrium with slower orbital speeds. 8.15.11.8.3 Stability in the solar system. Prevention of orbital collapse or ejection. The balance between centripetal and centrifugal forces ensures that larger planets farther out do not spiral inward toward the Sun. Smaller planets closer in are not flung outward by excessive orbital velocity. Harmonic orbital distribution. The spacing of planetary orbits aligns with the principle of relative equilibrium, creating a harmonious system where each planet occupies a stable position. By Ryan Carl Daly 26. Cookbook for the Universe. Relative to the Sun and neighboring planets. 8.15.11.8.4 Energy dynamics and resonance. Energy field interactions. Relative equilibrium incorporates not just mass and distance, but also the dynamic interplay of energy fields. Larger planets, with more substantial energy fields, stabilize at greater distances where their gravitational influence aligns with the Sun's field. Smaller planets interact more intensely with the Sun's immediate gravitational and electromagnetic fields. Orbital resonance. The balance described by m1d2 equals m2d1 also explains orbital resonance phenomena, where the orbital periods of planets and moons exhibit harmonic ratios, further stabilizing the system. 8.15.11.8.5 Key insights. Scaling of forces. The equation m1d2 equals m2d1 highlights how gravitational and centrifugal forces scale with mass and distance, ensuring proportional relationships across the solar system. Systemic harmony. Relative equilibrium underpins the stability and predictability of planetary orbits, contributing to the solar system's long-term coherence. 8.15.11.8.6 Broader implications. This principle extends beyond gravitational mechanics to include interactions of electromagnetic and other forces, offering a more holistic view of celestial dynamics. In summary, relative equilibrium provides a unifying framework to understand how planetary masses and distances work in tandem to maintain the dynamic yet stable structure of the solar system. It bridges classical gravitational theory with a more comprehensive perspective on energy and motion. 8.15.11.9 Relative equilibrium in the solar system. The principle m1d2 equals m2d1 illustrates the dynamic balance that governs the arrangement and stability of planetary orbits within the solar system. This formula. By Ryan Carl Daly 27. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe encapsulates how mass and distance interplay to achieve a state of equilibrium for celestial bodies influenced by the Sun's gravitational force. 8.15.11.9.1 Key implications of the relationship. A. Larger masses at greater distances. The relationship implies that planets with greater mass m require proportionally greater distances d from the Sun to maintain equilibrium. Jupiter, as the most massive planet, stabilizes at a far orbit due to its significant gravitational influence and relative energy. Smaller planets like Mercury and Earth orbit closer, where their smaller masses achieve balance under stronger gravitational pulls. B. Proportional balance between mass and distance. The equation ensures proportional scaling. Planets with higher mass exert and experience stronger gravitational forces, but at greater distances. The force diminishes appropriately to sustain a stable orbit. 8.15.11.9.2 Balancing gravitational and orbital forces. A. Centripetal force. The Sun's gravitational pull acts as the centripetal force that holds planets in their orbits. This force diminishes with the square of the distance 1d, meaning distant planets experience weaker pulls. B. Centrifugal force. A planet's orbital motion generates a centrifugal force that counteracts the Sun's gravity, increasing with the planet's velocity. C. Relative equilibrium demonstrates that closer planets orbit faster to counteract stronger gravitational pulls. Farther planets orbit slower, maintaining balance despite weaker gravitational interactions. 8.15.11.9.3 Achieving stability in orbital systems. A. Prevention of collapse or ejection. Proportional relationships between mass and distance ensure larger planets remain stable without spiraling inward. Smaller planets avoid being ejected by their own orbital velocity. By Ryan Carl Daly 28. Cookbook for the Universe. B. Distribution of orbital distances. The spacing of planets is a natural result of relative equilibrium. Inner planets form compact orbits due to their smaller masses and stronger gravitational ties. Outer planets stabilize in wide orbits, supported by their greater masses and reduced gravitational pull at those distances. 8.15.11.9.4 Key Insights. A. Gravitational balance. The equilibrium described by m1d2 equals m2d1 reflects the dynamic forces at play, ensuring stability across the solar system. B. Scaling of orbital forces. The interplay between gravitational and centrifugal forces scales with the relative masses and distances of celestial bodies. C. Long-term stability. This principle explains the enduring arrangement of the solar system, where each planet's orbit reflects a balance of forces tailored to its mass and distance. In summary, relative equilibrium, as expressed by m1d2 equals m2d1, provides a robust framework for understanding the hierarchical distribution and stability of planets in the solar system, highlighting the intricate balance of forces that governs celestial mechanics. 8.15.11.9.5 Gravitational field strength. The Sun's gravitational influence diminishes with the square of the distance from it, following the inverse square law F1d proportional to 2. Smaller planets having lower masses can maintain stable orbits closer to the Sun, as their reduced mass requires less gravitational force to achieve equilibrium. Larger planets, possessing significantly greater mass, experience a stronger gravitational pull. To prevent spiraling into the Sun, they must orbit farther away, where the gravitational force weakens sufficiently to sustain a balanced trajectory. By Ryan Carl Daly 29. Aka, Essay on Relative Gravity to describe the mechanics of the universe. Orbital velocity. Orbital velocity v proportionals, where mr is inversely proportional to distance. Smaller planets, closer to the Sun, move at higher velocities, enabling them to maintain equilibrium at shorter distances. Larger planets orbit more slowly due to their mass, requiring greater distances to achieve a balance between their velocity and the Sun's diminished gravitational influence. 8.15.11.9.6 Angular momentum conservation. Larger celestial bodies carry significantly more angular momentum, expressed as L equals mvr. To conserve angular momentum, they must orbit at greater distances, reducing their velocity r1v while sustaining equilibrium with the Sun's gravitational force. Proportional. This principle explains why planets like Jupiter and Saturn, with their immense mass, occupy orbits far from the Sun. 8.15.11.9.7 Relative equilibrium as a governing principle. Using the relationship m1d2 equals m2d1. For larger bodies, e.g., Jupiter, the increased m1 planetary mass requires a proportional increase in d2 distance from the Sun to maintain equilibrium. This ensures that the gravitational field strength is appropriately adjusted for the planet's greater mass. For smaller bodies, e.g., Mercury, the lower m1 permits a smaller d2, allowing it to remain closer to the Sun while maintaining equilibrium. 8.15.11.9.8 System-wide implications. Orbital resonance and spacing play a crucial role in the stability of the solar system. The greater distances of larger planets result in fewer disruptive gravitational interactions with smaller, inner planets. This separation contributes to the solar system's overall stability. resonance effects, such as the well-documented 5-2 resonance between Jupiter and Saturn, arise naturally because the spacing of planetary orbits adheres to principles of relative equilibrium. By Ryan Carl Daly, 30. Cookbook for the Universe. These resonances represent synchronized interactions where the gravitational influences of planets reinforce rather than destabilize their orbits. 8.15.11.9.9 Formation and migration. During the early stages of solar system formation, larger planets, capable of accreting more mass due to their stronger gravitational pull, naturally formed farther from the Sun. These outer regions provided the necessary equilibrium conditions for massive bodies to stabilize without collapsing inward. Conversely, smaller planets with lower mass formed closer to the Sun, where tighter orbits could achieve equilibrium without being perturbed by the gravitational fields of larger planets. Over time, planetary migration adjusted the spatial configuration of the solar system. Gas giants may have shifted outward or inward due to interactions with the protoplanetary disk or other planets, finding their positions dictated by relative equilibrium. Inner planets eventually stabilized in their orbits once the larger bodies settled, reducing disruptive forces. 8.15.11.9.10 Exoplanetary systems. The principles of relative equilibrium extend beyond our solar system to exoplanetary systems. Massive gas giants are frequently observed farther from their stars, where equilibrium allows their formation and stability. Smaller rocky planets, on the other hand, often occupy closer orbits, reflecting the same dynamics observed within our solar system. 8.15.11.9.11 Analogy with the induction coil model. The solar system can be imagined as a sophisticated array of concentric coils. In this analogy, the Sun radiates gravitational and electromagnetic currents, acting as the primary source of energy and influence. Each planet functions as a secondary coil, dynamically resonating with the Sun's fields. Larger coils planets inherently require greater spacing to achieve resonance with the Sun's energy fields without causing destructive interference. Relative equilibrium acts as the organizing principle, defining the spatial distribution of planets and ensuring a dynamically stable system. By Ryan Carl Daly, 31. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. 8.15.11.9.12 Conclusion. In both classical and modern frameworks, larger bodies orbit farther from the Sun due to the interplay of gravitational strength, angular momentum conservation, and resonance effects. Relative equilibrium not only explains these dynamics, but also provides a universal framework for understanding orbital behavior across systems, offering profound insights into planetary formation, migration, and system stability. 8.15.11.10 Relative equilibrium as a framework for orbital dynamics. The relationship m1d2 equals m2d1 provides a foundational mathematical framework to understand the balance between mass, distance, and gravitational fields in the solar system. This principle explains not only the structured spacing of planets but also their unique orbital characteristics. Each celestial body finds its place within a finely tuned system of equilibrium, dictated by the interplay of these parameters. However, focusing solely on classical notions of mass might limit our understanding of these dynamics. By considering radiated fields of bodies treating the Sun and planets as entities that emit gravitational fields as energetic phenomena, the concept of equilibrium expands into a more dynamic and interconnected framework. In this perspective, radiated gravitational fields, each celestial body is not just a static mass but an emitter of gravitational energy fields. These fields interact continuously, shaping the spatial and temporal relationships among planets and the Sun. Dynamic interactions. The interplay of these radiated fields leads to a relative equilibrium that evolves over time. Rather than viewing the planets as mere masses in motion, we can see them as participants in an energy exchange that balances their positions and velocities within the solar system. Richness of interactions. By incorporating radiated fields, we account for variations in gravitational influence caused by phenomena like solar radiation pressure, planetary magnetospheres, and tidal interactions. This approach not only aligns with the principles of relative equilibrium, but also enhances our understanding of how these interactions stabilize the system. Resonant coupling. The dynamic exchange of energy among radiated fields can produce resonant effects, much like oscillating systems in physics. These resonances help maintain stability, as seen in orbital alignments, and the prevention of chaotic disruptions. Time-dependent evolution. As radiated fields fluctuate due to internal and external forces, for example solar activity, planetary alignments, the equilibrium adapts. By Ryan Carl Daly, 32. Cookbook for the Universe. This temporal aspect introduces a layer of complexity, emphasizing that equilibrium is not static, but a continuously recalibrated state. By shifting the focus from static masses to radiated fields, relative equilibrium becomes a tool for exploring the intricate dynamic relationships that govern the solar system. This perspective not only enriches classical mechanics, but also aligns with modern approaches that emphasize the interconnectedness of forces. Energy and time. 8.15.11.10.1 Relative equilibrium with radiated fields. Reframing M1d2 equals M2d1. We redefine M1 and M2 not as static masses, but as the radiated gravitational potentials EC or field strengths of the Sun and planets. D1 and D2 represent the distances at which these radiated fields achieve a balance point, or relative equilibrium, where neither field dominates. This approach emphasizes a dynamic interplay of radiated fields, offering insights into the solar system's structure and interactions. 8.15.11.10.1.1 Gravitational influence as field-based. Field radiation and decay. Each celestial body radiates a gravitational field outward, diminishing in strength with the square of the distance 1d proportional to 2. Larger bodies emit stronger fields, requiring greater distances to achieve equilibrium with the Sun's radiated influence. Interacting fields. Planets and the Sun are not static masses, but interacting radiated fields, dynamically adjusting to balance across distances. These fields overlap and interact, creating stable equilibrium zones. 8.15.11.10.1.2 Why larger bodies orbit further. A. Radiated gravitational potential. Larger bodies, like Jupiter, radiate more significant gravitational fields, resulting in an expansive zone of influence. These bodies require larger orbital distances to balance their radiated potentials with the Sun's diminished radiation at those points. B. Energy exchange between fields. The Sun and planets exchange gravitational energy. For larger planets, greater distances prevent overlap or resonance instabilities between their stronger. By Orion Carl Daly 33. Aka. Essay on Relative Gravity to describe the mechanics of the universe. Fields in the Sun's. C. Field geometry and decay. Gravitational fields are spherical, and their intensity decays with distance proportional to 1d. Larger bodies stabilize at farther points where the Sun's radiation sufficiently weakens to match their radiated strength. D. Field superposition and resonance. The radiated fields of planets and the Sun overlap in a superposition. Equilibrium is achieved at a distance where their fields harmonize without destructive interference. 8.15.11.10.1.3 Expanding beyond mass. By treating M1 and M2 as radiated gravitational fields rather than classical masses, relative equilibrium becomes a more dynamic framework. A. Radiated energy. Each planet radiates gravitational energy proportional to its mass energy equivalence M equals EC. Larger planets emit stronger fields, requiring more distant equilibrium zones. B. Temporal frames. Each celestial body operates within its unique time-space frame, influencing how it interacts with others. These frames converge at the balance point determined by radiated field intensities. C. Field superposition. The equilibrium distance d is where the Sun's radiated potential equals that of the planet, creating a dynamic balance of forces. 8.15.11.10.1.4 Solar System as radiated interactions. A. Inner planets. Smaller planets like Mercury and Earth with weaker fields achieve equilibrium closer to the Sun, where its radiation dominates. B. Outer planets. Larger planets like Jupiter and Saturn, radiating stronger fields, stabilize farther out where their fields balance the Sun's weaker outer radiation. C. System-wide balancing. Orbital spacing emerges naturally from the interaction of radiated fields, with resonances dictating stability and alignment. 8.15.11.10.1.5 Induction coil analogy for radiated fields. A. Sun is the primary coil. Radiates gravitational energy akin to a current, establishing the overarching field geometry. By Orion Carl Daly 34. Cookbook for the Universe. B. Planets as secondary coils. Induce their own gravitational fields in response, with strengths proportional to their mass-energy equivalence. C. Equilibrium as energy transfer. The balance point represents the stable transfer of energy between the Sun's field and each planet's radiated field. 8.15.11.10.1.6 Implications of gravity as an electromagnetic-like force. A. Gravity is radiated interaction. In this model, gravity behaves like an electromagnetic force, involving radiated fields that interact dynamically rather than acting as static poles. B. Wave-like behavior. Gravitational forces may involve oscillations in waveforms akin to electromagnetic fields. This suggests gravity could be an exchange of energy similar to currents or waves rather than merely a force acting at a distance. C. unified forces. This perspective hints at a deeper connection between gravity and electromagnetism, potentially bridging gaps in understanding between classical mechanics, relativity, and quantum physics. By reinterpreting gravitational forces as radiated fields, we move from treating celestial bodies as static masses to dynamic, energy-radiating entities. This enriched framework aligns with the principle of M1D2 equals M2D1 and deepens our understanding of the solar system as structure and dynamics. 8.15.11.11 Applying relative gravity and relative equilibrium to galaxies. The relative gravity and relative equilibrium framework offers a dynamic approach to understanding galaxies, where forces are no longer isolated gravitational effects but interacting fields within a shared space-time manifold. This perspective enriches the classical understanding of galactic dynamics, emphasizing interactions between radiated gravitational potentials and relative equilibrium zones. By Ryan Carl Daly 35. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. 8.15.11.11.1 Relative Forces in Galaxies. In establishing how relative gravity can be applied to a solar system, we can extend its application to galaxies, which are far more complex systems with much larger scales. Galaxies, like solar systems, consist of many bodies, stars, dark matter, etc., that interact through relative forces. Gravity, electromagnetic forces, and even the effects of dark matter would all play a role in maintaining the relative equilibrium of the galaxy. Dynamic balance of forces. Relative forces, gravitational and electromagnetic, interact across vast distances, creating equilibrium zones where bodies find stable orbits and alignments. Field interactions across scales, dark matter, radiated gravitational energy, and electromagnetic forces contribute to the galactic structure, ensuring a cohesive yet flexible system. By applying relative gravity and its principle of relative equilibrium, we can see the Milky Way as a dynamic system driven by the mechanics of its black hole, the torque of its spiral arms, and the equilibrium zones of its orbiting stars and systems. Each heavenly body contributes to a balance of radiated gravitational potentials, creating the galaxy's iconic structure and motion. At the universal scale, the Milky by Ryan Carl Daly 36. Cookbook for the Universe Way participates in a grander equilibrium of galaxies, filaments, and cosmic induction currents, all linked by the shared principles of radiated gravitational energy and equilibrium. 8.15.11.11.2 Applying relative gravity to the Milky Way. A. Relative gravity and relative equilibrium in the galactic context. The model M1D2 equals M2D1, where gravitational interactions are viewed as field-based rather than mass-based, aligns perfectly with the Milky Way's rotational and structural characteristics. B. Gravitational fields as radiated energy. The Milky Way's central supermassive black hole Sagittarius serves as the primary field generator, radiating intense gravitational energy that interacts with the fields of stars, solar systems, and interstellar matter. Each heavenly body contributes to a system-wide balance of relative gravitational potentials. C. Galactic torque and orbital dynamics. Stars and solar systems orbit along the galactic disk, aligning with the threads of torque created by the interplay of the black hole's field and the distributed mass energy of the galactic disk. Larger systems or more massive clusters orbit farther, consistent with M1D2 equals M2D1, where larger M2 bodies require larger D1 distances to maintain equilibrium. 8.15.11.11.3 Spiral arms and equilibrium zones. The Milky Way's spiral arms reflect the dynamic equilibrium of relative gravitational fields. Field superposition. The overlapping radiated fields from stars and clusters create torque along the spiral arms, maintaining their iconic shape. Equilibrium zones. Stars align along equilibrium paths dictated by the radiated potentials, with inner stars orbiting faster and outer stars slower to sustain the galaxy's balance. 8.15.11.11.4 Interplay of dark matter. Dark matter's gravitational influence creates an extended halo, stabilizing the galaxy's outer edges and preventing it from tearing apart. A. Impedance and gravitational waves. Dark matter acts as a damping medium, modulating gravitational waves and reinforcing stability in equilibrium zones. By Ryan Carl Daly 37. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. B. Extension of relative equilibrium. The interaction between visible matter and dark matter expands the equilibrium framework, ensuring the galaxy's structure across larger scales. C. Dark matter in this context is not just a mysterious substance but could be seen as a force acting relative to the matter we observe, influencing the galaxy's structure through its interaction with normal matter. Instead of just viewing gravity as an attractive force, relative gravity would view it as part of a broader network of forces that interact within the galaxy. The impedance in this system could be represented by the resistance to the motion of stars and other bodies, not unlike the electromagnetic induction model applied to the solar system. 8.15.11.11.5 The Milky Way. In universal context, the Milky Way does not exist in isolation. It participates in a broader network of cosmic structures, including neighboring galaxies, filaments, and cosmic voids. A. Intergalactic equilibrium. Galaxies themselves radiate gravitational fields that interact with others, forming equilibrium zones at universal scales. B. Cosmic induction currents. The galaxy aligns with larger cosmic flows, driven by the interplay of gravitational potentials across filaments and voids. 8.15.11.11.6 Field-based insights into galactic structure. By treating galaxies as systems of radiated gravitational energy, we can derive richer explanations for their dynamics. A. Rotational curves. The flat rotation curves observed in galaxies can be linked to the balance of radiated fields, incorporating dark matter's contribution as a stabilizing factor. B. Spiral arm formation. Torque from the interplay of radiated fields and dark matter influences creates the galaxy's iconic spiral structure. C. Cluster interactions. Galaxy clusters align and interact based on the radiated energy fields of their constituent galaxies, reinforcing cosmic equilibrium. 8.15.11.11.7 Relevance of relative gravity at galactic scales. A. Unified dynamics. Relative gravity provides a cohesive framework that connects individual stars to the galaxy and galaxies to the broader cosmos. B. Scalable principles. The same equations that describe the Sun-Earth system m1d2 equals m2d1 extend to. By Ryan Carl Daly 38. Cookbook for the Universe. Galaxies, revealing universal principles of balance and interaction. Applying relative gravity and relative equilibrium to galaxies transforms our understanding of these vast structures. By viewing galaxies as systems of radiated gravitational energy and dynamic equilibrium, we uncover the intricate interplay of forces that maintain their stability and align them within the broader cosmic fabric. This perspective not only enriches classical astrophysics but also bridges the gap between local and universal dynamics. 8.15.11.12 Gravitational forces in galaxies. Galaxies as colossal systems of stars, interstellar gas, and dark matter are the quintessential stage to explore relative gravity and its dynamic interplay of forces. Their immense scale and structural complexity demand a nuanced perspective that moves beyond traditional gravitational models. Instead, they call for an integrative view of relative forces that include gravitational fields, electromagnetic interactions, and the enigmatic contributions of dark matter. 8.15.11.12.1 Galaxy formation and dynamics. In the relative gravity framework, a galaxy can be envisioned as a vast spatial induction engine where forces behave like alternating currents. Gravitational interactions within galaxies are modulated dynamically, with the spiral arms representing resonance patterns rather than static structures. These arms serve as pathways of relative equilibrium where radiated fields from the central black hole and the galaxy's distributed mass coalesce into spiraled symmetries. A. Formation of galactic arms. Stars and gas in the arms are dynamically balanced within the galaxy's gravitational field. As mass coalesces under gravitational potentials, it aligns along these arms, forming dense star-forming regions. New stellar systems emerge as the galaxy evolves, keeping the arms dynamic and self-sustaining. B. Role of dark matter. Dark matter, often considered a passive gravitational influence, is reframed as a dynamic participant providing impedance within the galaxy's induction engine. It helps stabilize the galaxy's structure by modulating the relative forces acting on stars and gas clouds. By Ryan Carl Daly 39. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe. C. Central black hole as a driver. The supermassive black hole at the galactic center radiates intense gravitational energy, anchoring the system and acting as a resonance hub. Its interaction with the galaxy's distributed mass creates the torque necessary for spiral arm formation and motion. 8.15.11.12.2 Synchronization in galactic motion. Galactic stability relies on the synchronization of its diverse components. Relative gravity introduces the idea of spatial time as a unifying construct that governs how stars, gas, and dark matter interact coherently. A. Interconnected reference frames. Stars and stellar systems operate within overlapping reference frames that synchronize their motions despite individual chaos. This synchronization prevents the galaxy from devolving into disarray, maintaining its iconic spiral or elliptical shape. B. Dynamic feedback mechanism. Just as planets oscillate in solar systems, stars within galaxies experience oscillatory motion influenced by gravitational potentials and radiated fields. This feedback adjusts the galaxy's structure in real time, ensuring its long-term stability and coherence. 8.15.11.12.3 Extending relative gravity principles. Scaling up from solar systems. Relative gravity applies its principles to galaxies by focusing on the interactions between massive components like stars, black holes, and dark matter halos. A. Field-based interactions. The galaxy's gravitational dynamics are driven by radiated fields rather than isolated masses. These fields superimpose and interact, creating zones of relative equilibrium that stabilize stellar orbits and galactic rotation. B. Interstellar currents and cycles. Interstellar gas, dust, and stars contribute to a continuous cycle of force exchange akin to an alternator system. The galaxy regulates its mass-energy distribution through this cyclic mechanism, ensuring longevity and evolution. By Ryan Carl Daly 40. Cookbook for the Universe 8.15.11.12.4 Galactic Structure and Evolution. The galaxy's structure is a manifestation of relative equilibrium in action. Stars, gas, and dark matter maintain dynamic stability by responding to the relative forces radiated by the system's components. A. Supermassive black hole as resonance center. Acts as a stabilizing force for the galaxy, much like a transformer core in an induction system. Regulates the energy distribution. Ensures coherence of the galactic spiral arms. B. Star movement and dark matter interaction. Stars near the galactic core move rapidly due to the intense gravitational field, while outer stars orbit more slowly. Stars near the galactic core move rapidly due to the intense gravitational field, while outer stars orbit more slowly, demonstrating the equilibrium between mass and distance as per relative gravity principles. C. Dynamic expansion and contraction. Dark energy and other cosmic forces could influence the galaxy's gradual expansion or contraction, suggesting that galaxies undergo cyclic processes akin to oscillatory systems. 8.15.11.12.5 Toward a universal model. Relative gravity positions galaxies as dynamic systems where gravitational forces are not the sole actors but part of a larger interplay of radiated fields, electromagnetic forces, and dark matter. By doing so, it bridges classical mechanics with modern astrophysical insights. A. Cyclic galactic processes. Just as solar systems oscillate, galaxies might undergo long-term cycles of formation, interaction, and dissolution. This perspective aligns with theories of galactic evolution and the life cycle of stars within them. B. Intergalactic applications. Scaling up further, relative gravity can explain the interactions between galaxies, their clustering into superstructures, and their participation in cosmic filaments. These systems operate under the same principles of radiated equilibrium and dynamic feedback. In galaxies, the principles of relative gravity and relative equilibrium reveal a universe of dynamic interactions and harmonic balances. By treating stars, black holes, and dark matter as components of a field-driven system, the theory provides a fresh lens to view galactic motion, structure, and evolution. This understanding underscores the interconnectedness of cosmic systems, demonstrating how forces radiate, interact, and sustain the universe on every scale. By Ryan Carl Daly 41. Aka, Essay on Relative Gravity to Describe the Mechanics of the Universe 8.15.12, about celestial mechanics. Relative gravity introduces a paradigm shift in how we understand celestial mechanics by emphasizing energy field interactions over traditional gravitational force models. This approach not only redefines the nature of orbits and planetary formation, but also provides a novel perspective on astrophysical phenomena like gravitational waves. 8.15.12.1 Orbital Dynamics. Relative equilibrium recasts the orbits of celestial bodies as dynamic balances of energy fields rather than mere gravitational attractions. A. Field interactions versus gravitational pull. In traditional Newtonian mechanics, orbits are determined by the balance between gravitational pull and centrifugal force. In the relative gravity framework, these orbits emerge from radiated energy fields interacting dynamically, where gravitational forces are a manifestation of overlapping energy potentials. B. Relative equilibrium. Orbits are stabilized through the harmonic interaction of radiated fields, which adjust continuously to maintain equilibrium. Larger bodies emit stronger fields, requiring greater distances for equilibrium, while smaller bodies stabilize closer to the central source. C. Impact on orbital stability. Resonance effects, such as those observed in the orbital relationships of Jupiter's moons, arise naturally from the alignment of overlapping energy fields. This perspective aligns with observed phenomena like orbital migration, where planets shift positions due to energy field redistributions. 8.15.12.2 Planetary formation. Relative gravity offers insights into how relative energy fields influence the clustering and stabilization of celestial bodies during planetary formation. A. Clustering of matter. As interstellar gas and dust interact within a protostar's radiated energy field, regions of higher field intensity act as attractors, Clustering matter into protostellar. By Orion Carl Daly 42. Cookbook for the Universe. And protoplanetary disks. These energy gradients create zones of relative equilibrium where matter coalesces into stable bodies. B. Formation of orbital hierarchies. The varying intensities of radiated fields influence the distribution of planets, with larger bodies forming farther out due to their stronger radiated energy potentials. Inner planets with lower mass energy equivalents stabilize closer to the star where the field gradients are steeper. C. Self-regulating dynamics. The formation process is inherently self-regulating, with energy fields dynamically redistributing to accommodate the evolving mass energy configurations of forming planets and moons. 8.15.12.3 Astrophysical phenomena and gravitational waves. Relative gravity reinterprets gravitational waves as oscillations within overlapping energy fields, shifting the focus from spacetime curvature to dynamic field interactions. A. Gravitational waves as energy oscillations. Traditional relativity views gravitational waves as ripples in spacetime caused by massive bodies in motion. Relative gravity suggests these waves are vibrations in radiated energy fields, propagating through the dynamic equilibrium between interacting bodies. B. Implications for wave detection. Observations of gravitational waves, such as those detected by LIGO, could be reinterpreted as measurements of field oscillations rather than spacetime distortions. The frequency and amplitude of these waves would reflect the harmonics of the interacting energy fields. C. Field overlaps and resonances. Phenomena like black hole mergers could generate intense overlapping energy fields, creating resonance patterns observed as high-amplitude gravitational waves. These events would represent a temporary breakdown and subsequent restabilization of relative equilibrium. By Orion Carl Daly 43. Aka. Essay on Relative Gravity to describe the mechanics of the universe. 8.15.12.4 Implications of relative gravity for celestial mechanics. A. Broader framework. By focusing on energy field interactions, relative gravity provides a unified framework for understanding phenomena across scales, from planetary orbits to galaxy formation. B. Revisiting classical mechanics. While classical mechanics explains many aspects of celestial motion, integrating energy fields into the analysis enriches our understanding of dynamic interactions. C. Future directions. Exploring the role of relative energy fields in phenomena like dark matter and dark energy could further expand the applicability of this framework, offering deeper insights into the universe's fundamental mechanics. In summary, relative gravity redefines celestial mechanics by emphasizing dynamic energy field interactions, offering a cohesive explanation for orbital dynamics, planetary formation, and astrophysical phenomena. This perspective not only aligns with observed data, but also opens new avenues for exploring the cosmos. 8.15.13 Dark matter and energy. Relative gravity proposes a compelling reinterpretation of dark matter and dark energy, viewing them as manifestations of undetected energy gradients that influence observed mass distributions and gravitational dynamics. By emphasizing the field nature of mass and force, relative equilibrium bridges the conceptual divides between classical mechanics, general relativity, and quantum field. By Orion Carl Daly 44. Cookbook for the Universe Theory, offering a unified framework for understanding these enigmatic phenomena. 8.15.13.1 Dark matter, undetected energy gradients and gravitational influence. A. Energy gradients as a proxy for dark matter. Traditional astrophysics explains the gravitational effects of dark matter as arising from invisible mass. Relative gravity reframes this, suggesting that undetected energy gradients may exert gravitational influence without requiring physical mass. These gradients could arise from interactions of radiated fields or energy potentials that align and reinforce gravitational effects in galactic halos and intergalactic structures. B. Observed effects of dark matter. The rotational curves of galaxies, which remain flat at large distances from the galactic center, are traditionally attributed to dark matter. Relative gravity posits that these rotational anomalies are the result of energy field interactions extending beyond the visible matter of the galaxy, maintaining equilibrium through dynamic field gradients. C. Field-based interpretation. Dark matter may represent localized enhancements of gravitational fields, where overlapping energy fields create regions of intensified force. This view eliminates the need for an invisible substance, instead attributing the effects to the harmonics of radiated fields from stars, black holes, and interstellar matter. 8.15.13.2 Dark energy. Expanding the universe through field interactions. A. Acceleration of cosmic expansion. Dark energy, as described in classical cosmology, drives the accelerating expansion of the universe. Relative gravity suggests this phenomenon could be the result of energy. By Orion Carl Daly 45. Aka. Essay on relative gravity to describe the mechanics of the universe. Gradients propagating through the manifold of space-time, pushing matter outward in a self-regulating equilibrium. B. Field dynamics and expansion. The universe's expansion might be governed by the interplay of radiated fields at cosmic scales, where energy gradients induce repulsive forces analogous to electromagnetic field interactions. This dynamic interaction aligns with the principles of relative gravity, which emphasize the role of field-based forces in shaping large-scale structures. C. Cosmic equilibrium. Dark energy could represent the residual energy fields of the universe, maintaining a balance that prevents collapse while promoting expansion. The relative equilibrium model accommodates this by framing the expansion as a consequence of balanced forces acting across vast distances. 8.15.13.3 Bridging theoretical frameworks. A. Classical mechanics. Relative gravity incorporates the Newtonian understanding of force and motion, but extends it by emphasizing radiated fields rather than point masses. B. General relativity. By reframing gravitational effects as interactions between energy fields, relative gravity complements Einstein's spacetime curvature model, introducing a more dynamic, field-oriented perspective. The concept of relative equilibrium aligns with the relativistic view of gravity as an emergent property of mass-energy distributions. C. Quantum field theory. The emphasis on energy gradients and field interactions provides a natural bridge to quantum field theory, where particles and forces are described as excitation S within fields. Dark matter and dark energy effects could correspond to quantum-level field interactions scaled to cosmic dimensions. 8.15.13.4 Implications for future research. A. Field-based observations. Instead of searching for elusive particles each WIMP or weakly interacting massive particles, researchers could focus on detecting the field harmonics and gradients that drive dark matter-like effects. By Orion Carl Daly 46. Cookbook for the Universe. Instruments like gravitational wave detectors could potentially identify these field dynamics. B. Unified theory development. Relative gravity's emphasis on fields and equilibrium could provide the foundation for a unified theory that reconciles the macroscopic effects of general relativity with the microscopic interactions of quantum mechanics. C. Reinterpreting cosmic structure. By treating galaxies, clusters, and filaments as field-interacting systems, relative gravity opens new avenues for understanding the large-scale structure of the universe. 8.15.13.5 Dark matter in the framework of relative gravity. Dark matter and dark energy, in the framework of relative gravity, are redefined as undetected energy gradients and dynamic field interactions. This reinterpretation eliminates the need for hypothetical substances, emphasizing the field nature of mass and force. By bridging classical mechanics, general relativity, and quantum field theory, relative gravity offers a cohesive and innovative approach to understanding these fundamental cosmic mysteries. By Orion Carl Daly 47.